Hello guys, welcome back to our video. Now in this video we are going to be looking at the part 2 of safety instrumented system. Okay, now don't forget we are trying to demonstrate this scenario using our DCS simulator. So in the part 1 of this video we try to look at a scenario where we are transferring crude from the truck down to a storage tank using a pump. Now in part 1 we try to focus on 3 scenarios that involves the pump. Okay, now I mentioned in the part 1 of the video that in the part 2 we are going to talk more of the ESD. Okay, so let's just go to our simulator and then let's see what we're going to be learning in this video. So let's open our simulator. Alright, so this is our simulator, and like I mentioned, this is our tank farm. Now your tank farm, which has your storage tanks, is one of the most critical assets in a facility. Okay, it's very critical because any spill from any of your tanks, be it your crude tank, be it your naphtha, be it your diesel, be it your kerosene, any spill in any of this tank is going to cause a catastrophic scenario where we have fire incidents. We have a lot of incidents that can go wrong if there's a spill. So protecting these tanks is one of the most important safeguards. Okay, so we have to safeguard this tank farm. Right now, in doing that, we need a lot of layers of protection in order to safeguard our plants. Okay, now safeguarding a tank farm requires multiple layers of protection. I'm going to explain all these layers to you using this our DCS. All right, now let's look at this particular tank here. Now if you look at it closely, you see we have different layer of protection. So I will explain the one after the other. So number one we're going to be looking at is our ESDs, right? Emergency shutdown devices. Okay, now if you want to know more about this, I created a video about it. So if you go over to my channel, you see the working principles of shutdown valves. I use AutoCAD Plant 3D to do this modeling. Okay, hazardous intervention. So you can watch this video and you see the various parts of the ESD, and then the working principle is also stated out here, so you can do that quickly. So let's go back to our simulator. All right, now on this tank we have various things here that we need to discuss. So the first is we have level instrumentation. Okay, so for level instrumentation we have the low level and we have the high. The low level is level at the bottom of the tank. There's a particular margin that is set out to be the low level. Anything below that level is getting critical. Okay, then we have the high level, which is also a level at the top of the tank. Anything above that level is getting to a critical level. So that is in terms of the level instrumentation. Now next is the alarm. Now here you see we have the LALL, which is we can call it the level alarm low. Okay, now this level is a level after the low level. Now after that low level, and then if the pump is still working and is still taking out the products or the crude and it's coming down, it will get to a point where the level alarm low is going to start beeping and notifying the control room operators that there is something going on. All right, Now also we have the level alarm high. Now level alarm high is the level after the high level. Okay, now after the high level, and then if you are still filling the tank, it will get to a point where we will now get up to the level alarm high, right? Now that is a critical level. So after this level, and then maybe the control operator is still not doing anything, then we'll now get to what we call a trip. The SIS, the SIS system, is going to take over, and then a trip will occur. So if you look at this diagram, you notice that there is a line coming down to the valve. Okay, now this means that after this level, a command will be given to the shutdown valve for it to close. Okay, now that is when the SIS has taken over. So a SIS is actually a situation where a scenario is being addressed with the help of the logic controller, right, without the intervention of humans, or without the intervention of the control operator. Okay, so it will just close down the valve by itself. Now that situation is when the SIS has taken over. That is why they call it safety instrumented system. So if all the layers of protection are failed, that is going to be one of the final layers of protection to protect the tank from overfilling and then spilling the products in the atmosphere. Now peradventure, if this doesn't work, there are other layers of protection. There are what we call the bond wall. Okay, so the bond wall is actually there to also prevent the spill from spreading to other parts of the facility. Now another layer of protection is also here. I have what we call the gas detectors. Okay, so you have the gas detectors here, as you can see, GT, these are gas detectors. Now this is also a layer of protection. So if there is a spill and then the concentration of the gas in that particular area increases to a particular value, a set point, the detector is going to send a signal to the shutdown valve for it to trip. Okay, because that concentration has gotten to a point where the detector thinks that there is a spill in that environment and is going to trip the pump, the shutdown valve, and invariably trip the pump if it is programmed to trip the pump. All right, so this is actually what we are going to be doing in this course. Now we are going to demonstrate this. We are going to demonstrate this scenario with this DCS. But before we do that, in the part 1 of this video, I mentioned that there are 3 criteria that makes an equipment, or let's say a device, to be a SIF, safety instrumented function. Okay, which is actually what carry out the function of isolating or reducing the consequences when there is a scenario. So number 1 I mentioned is that it must have a sensor. Now in this our demonstration, we have what we have a sensor here, a transmitter. So the transmitter this transmitter can be here, and it's going to be using radio waves to detect the level. So when the level is coming up, it's going to be calculating the level. All right, and then the values okay, so it's going to be calculating the level, and then you see the values will be transmitted in their transmitters there. Okay, so the transmitters are going to be recording the level based on what this radio wave or any kind of transmitter here is going to be. So that's the sensor. All right, now that is number 1. Now number 2, I mentioned that we're going to be having a logic solver. Okay, now the logic solver is actually in the auxiliary panel. Okay, the E&I auxiliary panel. Now, what happens is that when the transmitter here reads the value in the tank, it will send it to the panel. Now the logic solver is going to look at it. It's programmed that when it gets to a particular level, it means it has to send a command down to the final element. Now the final element is our shutdown valve here. So it will come like this and send the signal to this guy. Alright, so I mentioned that we must have these 3 criteria for it to be a SIF: sensor, the logic solver, and the final control elements. Alright, now even if we get this correct, how do we ensure that the ESD is a SIF? Okay, now apart from these 3 criteria, we need to also understand that even with these 3 criteria, the shutdown valve can also or may not be a SIF, except other criteria are also met. So the first one is it must be independent. So like I mentioned, there are different layers of protection. Now this particular layer should be independent of the other layers. That's one. Secondly, it must be SIL-rated. Okay, I mentioned four level of SIL. I mentioned level 1, level 2, level 3, and level 4. So it must be in one of these categories. Okay, level 1 is the SIF might fail in between 10 to 100 years. Level 2, the SIF might fail from 100 years to 1000 years. Level 3 from 1000 years to 10,000 years. Level 4 from 10,000 years to 100,000 years. Okay, so that's that. Then now the next one is that it must be accredited. I think I mentioned this in the part 1 of this video. It must be proof, right? It must be proven that this ESD is actually working perfectly. Now the final one is that it must be managed under the SIL lifecycle using IEC 61511. So that's the standard for SIS. Now if you want to get more information about the SIF and the SIS, we can let me show you. So you can go to you can download these documents, standard, okay, IEC 61511 standards. So here we have 3 parts: part 1, part 2, part 3. That's for IEC 61511. So part 1 is just about let's see, definition, system instruments, safety instrumented systems for the process industry sector. It's talking about the framework, the definition, the system, the hardware and software requirements. That's the part 1. Now the part 2 is talking about functional safety, which is the safety instrumented systems for the process industry sector, and it's just about the guidelines for the application of IEC 61511. Now the third one is the guidance for the determination of the SIL required safety integrity level. Okay, now with this standard you can understand a lot about what you're talking about. Now we also have another standard, IEC 61508, and this has up to 7 parts. So you can go through, you can download them, and then you go through all the parts. So you can just read this and then you have a lot of ideas about SIS. So let's go back to our simulator. So what we'll do now is we're going to demonstrate a loading operation, and then we see if we can bring out some points from this operation. So let's go to our crude loading and let's load let's load okay, this time around let's load 60,000 liters. So 60,000 liters is like it's like 4 compartments, right? Okay, now next let's go to the pump, and before we do that, before we put on the pump, let's check our lineup. So this shutdown valve is open, so we'll trace it back to our tank. So this one should be open, so I open the shutdown valve here. Okay, so we are now properly lined up. So let's put on the pump. And before I put on the pump, I need to monitor. Okay, I'll put on the pump, and let's go to the tank. All right, so as you can see, we have our high alarm. Our high level indicator is showing that we are getting to a critical level. So the level is going up. Let's continue to observe. So currently we have passed one level protection, one layer of protection. So let's go to the second layer of protection. Okay, just be patient. Be patient. Okay, so let's say currently the control room operator has not seen that the level is the indicator is showing red, and maybe it's busy with other activities. So what's going to happen is that it will get to the next layer of protection. Now the next layer of protection, like we all know, is going to be the alarm. Okay, so when it gets to the alarm, what if the control room operator is sleeping at that time? Let's say maybe the time is around 3 a.m. in the morning, and he feels a bit sleepy, and then he falls asleep. So the level alarm is supposed to wake the control room operator up, so I can know that the level is very critical. Okay, so the next question is, what if? What if? Well, let's wait and see. Okay.
Warning, critical level. Warning, critical level. Warning, critical level. Warning, critical level.
Okay, so we've got
warning,
the next level
critical level.
If you listen critically,
warning,
you hear
critical level.
An alarm indicating
warning,
that the level
critical
is
level.
Level
warning,
critical. So that's
critical
the
level.
High alarm.
Warning, critical level.
That the level I've got into a critical
warning,
level.
Critical level.
Now at this point,
warning,
what if
critical level.
the operator is still
warning,
sleeping?
Critical level.
What if the
warning,
operator is still sleeping?
critical level. Warning, critical level. Warning, critical level. Warning, critical level.
Okay, so
warning, critical
see.
level.
It means
warning, critical level.
Avoided.
Warning,
next thing is
critical level.
If the
warning, critical level. Warning, critical level.
Take over because this
warning,
is that
critical level. Warning,
the operators
critical level.
Busy.
Warning,
there's nobody
critical level.
The situation, and then
warning,
there is a
critical level.
Is going to take place.
Warning, critical level.
If it doesn't
warning,
take
critical level.
Right. So the SIS
warning, critical level.
take over.
Warning,
Then
critical level.
Remedy the situation.
Warning,
So let's
critical level.
if that is going to happen.
Warning, critical level. 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 Warning, critical level.
Okay.
Warning, critical level.
Now if you go over to,
warning, critical level.
If you go over to the truck,
warning, critical level. Warning, critical level.
12,000 liters.
Warning,
in the truck.
critical level.
But the level here.
Warning, critical level. Warning, critical level.
Okay, so there's a trip. There's a trip of the pump. Now as you can see, the pump has tripped off, and then the level is still at 10,600 liters. So let's go.
Warning,
to the
critical level.
Okay, now also you see the pump. The pump is powered off. Now you see
warning,
shutdown valve
critical level.
Also closed.
Warning,
see the
critical level.
Increment.
Warning,
so what this
critical level.
Means is that
warning, critical level.
What this means is that our protection. What this means is that our SIS actually took over and then remedied the situation. All right. So we are going to look at three scenarios. Now, for the three scenarios, you are going to, think carefully and then give your response based on what you understand. According to what we've been discussing all along. So, but then before I give you the three scenarios, I need you to also understand something else. All right, I've given some criteria on how we can, call this a safe or not. Clearly, for this situation, this is actually a safe. Now, this can only be a safe if we accredit this particular situation to be a safe. Now, like I said, we have three layers. The first layer is a level instrumentation, high level, low level. That is one. The second one is alarm. That is two. The third one is a trip. Now, if you accredit the trip to be a safe, it means this ESD is a safe. Now, but what if we accredit a different device? What if we accredit a different device? What if we accredit the fire, the gas detector? What if I accredit the gas detector to be as part of this system? Then this is not a safe. This is going to be a BPCS. This is going to be just a basic process control system. All right. So we need to understand this. We need to accredit it. Now, where do we accredit it? We accredit it during the process hazard analysis or risk assessments. Okay. During when we are doing HAZOP, or let's say we are doing a LOPA. Now, during this period, this is when we can now accredit that this is going to be what is going to safeguard this area based on the hazard. Okay, because there are various hazards that we are going to be looking at, right? So based on the hazard, we can accredit that this strip is going to be the safeguard for this particular environment, or let's say this fire detector is going to be, or gas detector is going to be the safeguard. Okay, so I will give an example on this scenario. So when I was a control room operator, there was a particular night that all of a sudden one of the ESD just tripped. Okay, now the ESD tripped, and then what happened was that the level of the tower, started building up. So and also the flow rates for residue going to the tank was not working. It was showing 0. That's because there was a blockage of the flow of residue down to the tank. So there was nothing there. So we had to you had to troubleshoot, you had to check to know what is causing it. Now after some period of back and forth, we trace the line and all the rest. We'll check the air coolers if the air coolers was blocked and all the rest. Then at the end of the day, we'll notice that there was a trip on this particular ESD, right? This ESD here, there was a trip. Okay, now what caused the trip was the level got to a particular level where it had to trip. Now the level was very high, so we are hoping, we are preparing to load residue to our residue trucks. Okay, so while we are preparing to do that, this guy tripped. Okay, now after that day, an instrumentation engineer was called to actually come and bypass the sensor, the let's say the sensor, to bypass it, not the sensor, to bypass the trip, to remove the trip, so that there is no trip that is supposed to trip the ESD whenever there is a high situation. Okay, now after that incident, we are working with without the trip, and then when the level gets high, what to do is that the DCS operator or the panel operator will actually manually close it, right? Manually close it. Now of course we did not allow it to get to that level again. We are very conscious of the level because we know that there is no trip. Okay, now as at that particular instant, we know that this shutdown valve is no longer a SIS, it's just a BPCS, just a basic process control system, just to close and open. Okay, now because the trip is no longer there, so you can't quantify it as a SIF. So hope you understand this particular explanation, right? So now when carrying out this risk assessment or process hazard analysis, we need to know that first of all, and this is what we're going to be doing when I give you these scenarios, we're going to follow these scenarios, follow this procedure, and then you think about it, and then you give a recommendation. Okay, so the first one is you need to identify the potential hazard. Okay, so what is your potential hazard here? Is, let's say, a spill, right? The spill of our product, that is the hazard. And right now, another thing again, after understanding or knowing the potential hazard, the next thing you can do is to analyze the system design. Now you analyze it by looking at the interlock, you look at the sensor, and then you look at the actuator. Okay, now the actuator is the top part of the shutdown valve. Okay, so the shutdown valve has an actuator, and it has your ball valve or your gate valve. So let's say ball valve. So the actuator is what controls the valve to close or open, right? So you need to look at the system design also, because like I mentioned, what if the interlock is from the gas detector and not from the trip, right? So the next is we evaluate the safety integrity. So the safety integrity is the SIL rating, C1, C2, C3. Now you need to look at which rating are you going to give this particular system. Is it C1, is it C2, is it C3, is it C4? Now if you analyze all this situation, you can now give your recommendation and say this is going to be a SIF or not. All right, so are you ready for the scenarios? Scenario number one, let's look at a situation where we have a tank fail, right? Tank fail. Okay, so just like the example that we did with our DCS simulator. So are we going to call that a SIF or not? Of course, you know the answer. I think I've given the answer already. Okay, so based on what we did, this is a SIF. But like I said, the trip has to be accredited. Okay, now if the trip is accredited, then you can call this a safe. So the next example, the next scenario number 2, is a spurious closure of the ESD. What I mean is that during the transfer, what if this our ESD closes, inadvertent closure due to, let's say, air supply or electricity or other stuff, but let's say the valve just closes it. What are we going to call it? Is it a safe or not? Okay, I believe if you watch the part 1 of this video, you can give your response to this. All right, so the next is scenario number 3. We have a transfer going on. This time around, we are transferring from this tank to this tank here from 305. Now, what if there is a low level? What if we got into a low level, and then we want to try to prevent a pump dry running? Okay, want to prevent a pump from running dry, like from sucking everything on the line, and then there's nothing going out. So what are we going to call it? Is it a safe or is it not a safe? Now, if you watch the part 1 of this video, I have already given you the response to this, but this is technical. And like I mentioned, I think if you think carefully, or just go back to the video and watch again, there are 2 sides to this response. Okay, and I'll just give you that. If you're trying to safeguard the pump, then that is not a safe. It is an asset protection. You're protecting the asset, the pump. But if you're talking about the buckling effects of the tank, of course, the thickness of the plates, the shell plate of the tank, they are very thick, 6 mm, 8 mm, 12 mm, depending on the height of the tank. We can have 16 mm, right? And then the higher the shell, the thinner the shell plate, right? But with that, the minimum shell plate is 6 mm, right? So 6 mm plates will actually find it difficult to buckle. But then, if it is a buckling effect, when there is a buckling effect, it means there might be a spill. So preventing a spill makes it a safe. But if you're trying to protect the pump that is doing the work, then it's not a safe. All right, so the next example is a line leak. All right, so let's take, for example, we are doing this transfer and there's a line leak somewhere here. Okay, now if there's a line leak somewhere, let me just say somewhere here, there's a line leak somewhere here, and then the crude spills all over this area. What's going to happen? The gas detector here is going to detect it. Now once it detects it, what it do is, if it is programmed to trip the shutdown valve, then it will send the signal to what we call the logic server, and the logic server will in turn send the signal to trip the ESD. Okay, so when that happens, it is called a safe. Okay, and also during the loading operation, what if there is a spill? Let me remove this. What if there is a spill? What if all the other layers of protection did not work? What if the operator did not respond to the high level indicator, and then the high level alarm, and also it goes to a trip and the trip did not work, and then there is a spill? Okay, so if there is a spill all around this environment, then the level the gas detector is going to detect it, and then it will send the signal to the logic controller. The logic controller will in turn send the signal to the ESD, and then it will trip. All right, so I hope we understand the basics of SIS, SIF, SIL, and then can talk about SIL assessment, SIL verification. So like I said, go to this code and then read about it, get more knowledge, and that's it. So I do hope that this demonstration give you a little understanding of how DCS is being operated with regards to safety of our tank, okay? Because that is actually the essence of this video. And the essence of this video is to use our DCS. Now this DCS is programmed with Excel. Excel is free, okay? So the essence of this video is to demonstrate how we can use this simulator to demonstrate the loading operation and then the safety aspect of the loading operation, okay, which is the safety instrumented system. So if you enjoyed this video, drop your comments. For the scenarios I give, if you don't understand anything, drop your comments. If I made any mistake, if there is correction and you want to do some clarification, drop your opinions in the comment section. So thank you for watching. See you in our next video.